This is lesson 45A, which is the first in a two-part lesson on adders. In this lesson we're going to design a circuit which will add two 4-bit binary numbers, and in part 2 of this lesson we'll talk about carry and overflow. Here's the truth table for a half adder. There are two inputs, A0 and B0, and two outputs, a sum and a carry. So if we add these numbers, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then we have 1 plus 1. So what's 1 plus 1? Well, in decimal, 1 plus 1 is 2, so in binary, 1 plus 1 would also be 2, that is 1, 0. So 1 plus 1 is 0 with a carry to the next bit. So in the truth table, 1 plus 1 is 0 with a carry. So notice that the sum is 0, 1, 1, 0. That's an exclusive OR gate. And the carry is 0, 0, 0, 1, which is an AND gate. So this circuit, made up of an exclusive OR gate and an AND gate, is the circuit for a half adder. Now, let's try to add two 4-bit numbers. Here's A and B. A is 5, B is 7. And so let's try to add these numbers. 1 plus 1, as we saw, was 0 with a carry. So we put the carry up here. Then 0 plus 1 is 1 plus 1, which is also 0 and a carry. 1 plus 1 is 0 and a carry, plus 1 is 1 and a carry. And then 0 plus 0 plus 1 is just 1. So sure enough, 5 plus 7 is 12. So that's how we add in binary. So you see the steps at every bit here. Call it, say, AI. This may be AI. And BI. So you add AI, BI, and in general you'll add a carry in, CI. And that will give you the sum SI with a carry out, CI plus 1. So let's look at the truth table for what's called a full adder, where we include the carry in. So the first 4 of these, with the carry in as 0, is just the half adder we had before, 0, 1, 1, 0, 0, 0, 0, 1. But now if we have the carry in, we have 0 plus 0 plus 1 is 1 and no carry. 0 plus 1 is 0 and a carry. 1 plus 0 plus 1 is 0 and a carry. And 1 plus 1 is 0 and a carry, plus 1 is 1 and a carry. So let's see if we can find a logic equation for the sum S. So you think maybe we should try a Carnot map to begin with. Min terms 1, 2, 4, and 7. Well, this doesn't look too promising. We have to draw 4 circles here, so we just have the min terms, so there's no simplification. So let's just write down the min terms. The first one would be not CI and not AI and BI. And then we'll have not C and A and not B. And then this one would be C and not A and not B. And the last one would be C and A and B. Okay, so we have this logic equation. So let's see if we can do a little bit of Boolean algebra and simplify it. We see there are some common terms here. So let's write it here. Look at the first two. What's common? Well, we have a not CI we can factor out. So here's a not CI and not A and B, or A and not B. And then we have these two terms, and here we can factor out the CI. So it's going to be or CI ANDed with not A and not B, or A and B. Okay, well, let's look in the parentheses here. Here we have not A and B, or A and not B. You should recognize that. You know what that is? Yeah, that's just the exclusive OR. A exclusive OR with B. AI exclusive OR with BI is not A and B or A and not B. So we can write this first term as not C ANDed with A exclusive OR with B. And what about the second term? Here we have not A and not B or A and B. You recognize that. That's just the exclusive NOR gate, not exclusive OR. So we can write not, we'll use just the tick mark here for not A exclusive OR with B, ANDed with CI. So can we simplify this? Well, look here. Here we have A exclusive OR with B. Let's just call that junk, say. And here we have A exclusive OR with B not. So this is not C and junk or C and not junk. Well, that's just the exclusive OR of C with junk. So what do we have? We have SI is just C exclusive ORed with AI exclusive ORed with BI. So this is sort of a reduced equation for the sum in terms of exclusive ORs. Well, let's go back and see if we can find a logic equation for the output carry CI plus 1 then. Let's try a Carnot map again. Here we have minterm 3, minterm 5, minterm 6, and minterm 7. So it looks like we have three circles here. We can draw a circle here, we can draw a circle here, and a circle there. Let's write the logic equation for CI plus 1 then. This is what? CI goes away, we end up with AI and BI. AI and BI, or here we have CI and BI. CI and BI, and this one will be what? CI and AI. Okay, so here is a reduced logic equation for the output carry. Let's sort of remember what that looks like. But it turns out that for our purposes, we might want to write it in a little different form. We saw when we drew the Carnot maps for the sum that we had ones on diagonals and they led to exclusive ORs. So maybe that'll happen here. Let's keep this one, but let's just draw a circle here and try to combine these and see what we get. So here we'll write the AI and BI like we had before, but here we'll just write the minterm, CI and not AI and BI, and here we'll just write the minterm, CI and AI and not BI. And now let's reduce this using some Boolean algebra. Here we can factor out the CI again. Let's see what we get. This is going to be AI and BI, or CI ANDed with not A and B or A and not B, which we recognize as the exclusive OR again. So here we have CI is AI and BI, or CI ANDed with A exclusive OR with B. Now, recall that this was the equation we had for the sum, and now we have this equation for the carry. So these two equations for the sum and carry out define a full adder, and we can now draw the logic equation. The sum is just CI exclusive ORed with AI exclusive ORed with BI. So these two exclusive OR gates make the output sum, and the output carry is just AI and BI, this AND gate, AI and BI, or CI ANDed with AI exclusive OR with BI. So let's look at this. You recognize what this is. Notice you have another one over here. Remember, this exclusive OR and AND gate were just the half adders that we had. So we have two half adders in this OR gate, and we can make the full adder. We can draw it this way. CI comes in here, AI and BI. The output of this half adder, this sum goes into here with the carry. Out comes the sum of the full adder, and you have this OR gate. So a full adder can be made from two half adders plus this OR gate. So now you see why we call them half adders. So we can draw a block diagram then of this full adder. Remember, inside here are those two exclusive OR gates and AND gates and OR gates. So here we have AI, BI, and CI in, and we have the sum SI out and CI plus 1. So we need one of these full adders for each bit. So to do a 4-bit addition, like we had here where we added the 5 and the 7 to get the 12, we need 4 of these. So A, this would be A3, A2, A1, A0, the 0, 1, 0, 1. The B3, B2, B1, B0 is the 0, 1, 1, 1. And we start with the rightmost bit, so we have a 0 carry coming in. A0, B0 is the 1 and 1. Out comes S0 here, and C1, so this is C1. Then the C1 gets added to A1, B1 to get S1 and C2 out. Then that gets added to A2 plus B2 to get S2 and C3 out. And then that gets added to A3 plus B3 to give S3 out, and plus a possible carry. In this case it was no carry, but in general you might have a C4 out. That would be the carry out of the full adder, of the 4-bit adder. Now, in part 2 of this lesson on adders, we'll talk more about the meaning of this carry out and also introduce the overflow bit.